Hello, you're watching Physics 2211 Lab 4 Oscillations by Sam Jabley. So for the introduction, in this lab the motion of a spring mass system is going to be investigated with the mass of the system swinging in an arc pattern in an oscillation. The purpose of this lab is to compare the data from the experimental portion of the lab to the computational model that was created to discern whether the spring mass system follows the energy principle. And the lab should show how Newton's second law can be equated with the energy principle and show how the equations such as the spring force can be relevant in the energy principle. So, before we get started, some details and results preview. The system is the mass, spring, and the earth, and the surroundings is everything else. There's no interactions with the surroundings. The experimental model is going to be a video that will be analyzed by the program tracker and will be used to plot data. The computational model will be created using GlowScript, and the results, the experimental model will obey the energy principle. So, some background physics. Newton's second law states that the net force is equal to the change in momentum over change in time. From this, and looking at a drawing of the model, you can discern that the net force equals the force of gravity plus the force of the spring, which you can sub in the known equations here. For the energy principle, a system's change in energy is the sum of the work done on the system by the surroundings plus heat. The surroundings does no work, so the change in energy is zero. From this, you get that the gravitational potential energy plus the spring potential energy plus the spring kinetic energy is equal to zero. And you can plug in the known equations here. The update formulas and the energy formulas here are also useful in this lab. So here's the experimental model that I did. I had to point mass track the center of mass of the object in each frame. And here you see the two plots of mass versus time in the x and y directions. And here's some extra stuff that I discerned from this data. Mainly F net and L naught and the period. So for the computational model, here I changed mass, initial position, spring constant, and relaxed length in the code. I set the values for the spring force formula. And then I set the formulas for kinetic, gravitational potential, spring potential, and total energy formulas right here. Then I set F grav, F spring, F net, ball.vel, ball.pos, position, and inserted the value for L, L hat, and S into the loop that updates. And then I inserted the update formulas and used them to calculate the energy changes down here. So, here is the computational model results versus the experimental model. Here you can see the computational model on the left with the spring and the mass system. And on the right you can see the model versus the experiment graphed. This is in the x position versus time, this is in the y position versus time. So, some possible errors. The data for the model and the experiment are very close to begin with, but they deviate from each other as time passes. And this is likely due to a few things. Starting off, the tracking error. I had to point track the center of mass of the object in each frame, and there was likely some errors there as I wasn't exactly on point, which is really hard to do since there was 90 to 100 frames, I believe. But in reality, the surroundings are actually doing work on the system, so that does affect the comparison, which is why they're very similar to begin with, but then they start deviating away from each other as time goes on. So, does the experiment satisfy the energy principle? As shown by the change in energy versus time graph here, yes, this experiment does satisfy the energy principle. The different energies computed by the computational model all cancel out at any given point, and it graphs such that delta E itself is constantly zero. This satisfies the energy principle such that the change in energy equals zero when the surroundings do no work on the system. So, the oscillation periods. Here I calculated the x and y directions by saying that 3 periods is equal to a value between the peaks of 3 separate wavelengths. And changing directions when calculating the periods would cause deviations in the periods, and that affects the graphs and what the spring potential energy may look like. Thank you so much for watching, and I hope you learned something today.